The overall goal of this procedure is to use Raman spectroscopy to determine the nanoparticle size distribution in a fast, reliable, and non-destructive way. This is accomplished by first acquiring the Raman spectrum of nanoparticles of interest. The second step is to analyze the measurement data and locate the subdistributions in it using the multi-particle phonon confinement model. Next, the mean size and the width factor of the subdistributions from the fitted model are determined. The final step is to use the obtained parameters to determine the actual size distribution of nanoparticles of interest. Ultimately, Raman spectroscopy is used to show that it is possible to determine the nanoparticle size distribution in a fast, reliable, and non-destructive way.
The main advantage of this technique over existing methods like transmission electron microscopy and X-ray diffraction is that Raman spectroscopy gives quick and reliable results in a non-destructive way, and it's available on demand in most of the laboratories.
Begin by synthesizing nanocrystals of interest. Deposit the silicon nanocrystals onto a glass substrate using plasma-enhanced chemical vapor deposition. Here, silicon nanocrystals are synthesized with an approximate size of 2 to 120 nanometers and a bimodal distribution in the ranges of 2 to 10 nanometers and 40 to 120 nanometers. Next, turn on the laser of the Raman spectroscopy setup and allow it to warm up for approximately 15 minutes in order for the laser intensity to stabilize. Make sure the laser and active lights are off before opening the door in order to be safe from the unwanted illumination of the operating laser. Next, press Door Release and open the door of the measurement chamber. Place the sample onto the sample holder stage. Select the 50x objective and focus on the surface of the nanocrystal powder. Then, close the door of the measurement chamber. Next, remove the shutter by clicking the Shutter Out button. The laser sign should now flash green and the active sign should blink red. From the live image, fine-tune the focus of the sample using the wheel manipulator until the smallest laser spot is observed on the live image. Then, from the measurement toolbar, select the New Spectral Acquisition option. From the pop-up window, set the measurement range to between 150 and 700 inverse centimeters. Set the time for the measurement to 30 seconds, the total number of acquisition at 2, and the percentage of the laser power to 0.5%, based on a 25 milliwatt laser. Next, start the measurement by clicking on the Acquisition Start button on the menu bar. After the measurement is finished, put the shutter in by clicking the Shutter In button. Save the data as both a WXD file and as a TXT file. The text file will be used for the analysis of the experimental data. Observe that the lights of the laser and the active are turned off. Then, press Door Release and open the door of the measurement chamber. Then, measure a bulk reference of the nanomaterial by repeating this process using a reference sample. From the peak position of the bulk material, estimate the relative shift. First, open the text files of the measurements for the nanocrystal measurement and the bulk reference. Before plotting the data, smooth them using cubic spline and normalize the data to 1 at their highest peak positions in order to have a good comparison of the relative peak shifts. Plot the silicon nanocrystal and reference silicon data. Determine the peak position of reference silicon and estimate the amount of the shift, if any, from the actual peak position of 521 inverse centimeters. Then, save the processed silicon nanocrystal data as a TXT file. Then, start the fitting procedure. For the fitting procedure, type the fitting function shown here into an analysis program such as Mathematica. Ensure that the interval for skewness is between 0.1 and 1.0, and the mean size interval is between 2 nanometers and 20 nanometers. For the fitting procedure, first import the normalized and corrected data as the input for the nonlinear fitting model using the import command. Press Shift and Enter to perform the fitting procedure. After that, insert the obtained values for the mean size and the skewness in the predefined generic distribution function shown here. Finally, highlight the size distribution equation shown here and plot the size distribution from 2 to 15 nanometers using the plot command as the lower and upper limits of the distribution. The particles in the sample shown here were measured via transmission electron microscopy and were found to have a bimodal size distribution of nanoparticles. The small nanoparticles were between 2 and 10 nanometers, and the large nanoparticles were between 40 and 120 nanometers. The analysis of the Raman spectrum reveals that the size distribution of small particles are indeed in the range of 2 to 10 nanometers. The distribution was found to be log normal with a mean size of 4.2 nanometers, with a skewness of 0.27. Raman spectroscopy is an ideal method to measure the slight size difference of silicon nanoparticles formed using two different flow rates of silane. When the flow rate was increased from 3 standard cubic centimeters per second to 10, the average particle diameter dropped and the skewness slightly increased.
Once mastered, this technique can be done in just a few minutes if it is performed properly.